All right, as we get started today, let's go ahead and take a look at page 289 in your textbooks. Page 289, word problem 13 you had for homework. You also have page 287, numbers 1 through 23, the odd. You're practicing multiplying radicals. We're going to get to those in just a moment. But starting with page 289, word problem 13. You even did number 25. You're a good man. Way to go above and beyond. Good job, Bracken. New favorite student. So 1 through 23, the odd. Hey, you know what though? Tell you what, if you got it right, I'll give you extra credit for it.
I got it wrong.
Oh, never mind that.
Because at the bottom of my notes, I put don't factor. So I don't think I factored anything.
Oh, that might be a problem. All right, number 13. We're going to start there, Brecken. Read number 13 for us, if you would, sir.
Tickets for each game in the holiday basketball tournament were priced at $3 for students and $5 for non-students. If 1,500 tickets for the championship game were sold for a total of $5,000, how many student tickets were sold?
All right, this is presumably like a college campus or something, surely. Though, well, I don't know. I mean, high schools, like the big public schools, you were going to them, they've got a few thousand kids at them, right? So it wouldn't be uncommon, actually, for 1,500 tickets to be sold. So anyway, holiday basketball tournament. You got two types of people coming to these games, or the championship game, and they are students and non-students. I should have just written not. Oh well, students and not. And there's a few different thoughts here that we might want to set up in a chart, Brecken.
Students are X, and non-students are Y.
And we're specifically referring to what about the students and non-students? How many of them, right? Not how much they're paying, but how many of them. In other words, we could say the number of students and non-students, because we know how much they each pay. We know the money associated with each. For the students, it's 5. There we go. See, I've done that whole money thing for years, Maddie, but now every time I say anything, Maddie. Anyway, and then of course, the next thought would be, well, if you've got X students paying $3 a piece, Y non-students for $5 a piece, then the there we go. Now there's two numbers, of course, that we haven't used yet, and there are some totals, if you will. What are those numbers?
1,500 tickets and $5,000.
Right, 1,500 tickets, which means 1,500 people, and $5,000, which of course is money. And so what are our two equations here, Bracken?
X plus Y equals 1,500 and 3x plus 5y plus 5y.
There we go. And again, one of the major mistakes that students will make is they'll put the 5,000 with the wrong one, the 1,500. Well, again, 1,500 is the number. Number plus number has to equal number. Money plus money has to equal money. And how many had the same system that Brecken had? All right, Maddie, what do we do next? To get 3x, 3y, and 4,500. Good choice. And of course, if you'd done 5, it would have been 7,500. Just put a line across the top. So anyway, and then what? Wow, that's really lopsided. All right, so that means that 250 non-students came. So presumably that's parents, guests, media, whatever. Which means pretty much everybody there was a student. How many students came? Back to Brecken.
417.
Well, how many total tickets were there? 1,500. And only 250 of those were actually non-students. So help him know how many students? 1,250 students came to that championship game. Did you get that answer also? All right, no clue what happened?
I have the answer written right here. I don't know why I wrote down 417.
417 is a very strange number, I'll grant you. But you have the 1,250 written, you just somehow 417 got written also for no apparent reason. Questions on this? Questions? All right, Brecken is now befuddled. Let's turn back to page, that's a word we don't use often enough, befuddled. Turn back to page 287, and let's take a look at numbers 1 through 23, the odd. Now we said to add radicals, Noah, the radicals have to be similar, which means they have to have the same radicand and the same index, right? To multiply radicals, Maddie, they don't have to have the same index and radicand. They don't have to be similar. Just like you can multiply dissimilar terms. What does have to be the same? Just the index. And in Algebra 1, we're so nice to you guys. They're gonna have the same index. It's great. In Algebra 2, not so much. And I am going to show you, just for curiosity's sake, what we would do. But again, in Algebra 1, you're not going to have to know how to work with differentiated indices. Looking at number 1, it really couldn't be any easier. So we better go to Noah. Noah, number 1, Noah, what'd you get for your answer? Square root of 42. And that doesn't reduce at the end, because that's when we would reduce, right, Brecken? We would not reduce at the beginning. We would wait till the very end to reduce just that one time. And yeah, square root of 42, and we're done. How about number 3? Brecken, initially when we multiply, we'll get number 3 from the homework.
150.
Well, not 150, but the square root of 150, right? Now, the difference between this and the last problem is this does reduce. I can factor the 150. What square do you think is in 150?
25 times 6.
Yeah, 25 times 6, so we could reduce our answer down to get?
5 square root of 6.
There we go. Now, did you actually have that answer? Kind of. Because you said at the beginning you didn't reduce, but you spat out 25 times 6 real quick. So I'm like, man, either he's really good with money, or he had it correct the whole time and didn't know it.
I wrote down 25 times 6 right here. So, and it said 150, and this one was 150, so I guess I did 1.
All right, let's go to number 5. Maddie, what'd you get for your answer? Square root of 33, and it doesn't reduce. We're done. Number 7, what did you get for your initial answer, Noah?
Square root of 15x to 9.
There we go. Now, can I factor a 15 in any way that helps me? Now, I mean, 3 and 5 is the only way to do it, and neither of those help. But I can do something with the letter, because the index right now is a, which can go into
9.
how many times?
4.
With, and so we can reduce our answer down to x to the 4th times the square root of 15x. Did anyone have that final answer on 7? Did we leave it as the square root of 15x to the 9th? Do we see now what to do at the end? Go ahead and reduce. Number 9, Brecken, what did you get?
3 times the square root of 10.
Yeah, and the 10 doesn't factor anything down in a way that helps me, so we'll just leave it 3 times the square root of 10. Number 11, Maddie, what did we get initially? And of course, Noah knows that 72 is 36 times 2, which is really helpful for square roots. But it's absolutely worthless for cube roots, so instead, Maddie, we'll go with what factors? Uh-oh, for a cube root? No, 36 is a great square, but it's a horrible cube. So instead, we should go with which of those is the cube? The 8, I can take the cube root of the 8 to get, and there was already 2 out here, so my answer, 4 times the cube root of 9. And did anyone get that final answer? All right, again, maybe just forgot to reduce at the end. How many at least have the 2 times the cube root of 72? All right, questions? And just again, be careful, make sure we're pulling from the right list. If it's square roots, this list, cube roots, you got that much shorter list to work with. Numero 13-0, Noah-O, what'd you get initially? Square root of 98, which does factor into
49 times 2.
So our final answer?
7 times square root of 2.
Good, 7 times the square root of 2. How many had that for 13? Questions, 13, did you at least get square root of 98? Okay. Number 15, we have radical expression being squared. And there's a couple ways to work with this. One method would be to simply write it a second time and go ahead and do the multiplying like we've been doing. But I told you before that when you square a radical, you're going to start by squaring the coefficient class to get 4. And then I told you to write this statement in your notes yesterday. When you square a square root, you get the radicand. Thank you, Brecken class. When you square a square root, you get the radicand. Say the whole thing with me now. When you square a square root, you get the radicand. Next year in Algebra 2, we're going to work with even more radicals. And just having that statement at the top of your head is going to help you a lot. In fact, by the way, when you cube a cube root, you know what you get? The radicand. You know what you get when you raise a fifth root to the fifth power? The radicand. Anytime, because you're just doing an opposite operation, right? So when you square a square root class, get the radicand. So when I square the square root of 3 class, I just get 3, the radicand. So square the 2, get 4, square the square root of 3 to just get 3, and then my answer class should have come out to 12. Now again, is it wrong to say 2 squared to 3 times 2 squared to 3 gives 4 times squared to 9? Hey, that's 3! That's 4 times 3! That's 12. No, nothing wrong with that. Maybe a little goofy sounding, but nothing wrong with doing it that way, but with what we're about to do here in just a moment, is certainly what we'll do in Algebra 2 on a greater scale. So inefficient. We don't want to do it that way. We like math to be easy because we are lazy. So let's find easy ways to do things. Questions 15. How many did end up with 12 regardless of how you did it? All right, number 17. Here we've got multiple radicals, right? There's 3 of them, not just 2 of them. That's okay. Multiply all your coefficients together, multiply all your radicands together, and then reduce at the end. So what do we get for our initial answer on 17? And let's see, whose turn are we at now? Brecken. Number 17, what'd you get for your initial answer?
-12 times the square root of 300.
Excellent. -12 times the square root of, 300 is right. Sorry. -12 times the square root of 300. Now, Brecken, there is a square in 300 that's just screaming at us right now.
No.
I mean, 25 is there, but it's not screaming. 300. Class? 100.
Oh, that's a square.
It's a very useful square, especially for dealing with hundreds, right? So 100 times 3. Now, granted, okay, 25 would work. 25 times 12, and then 12 factors into 4 times 3. But man, is this so much more efficient? Again, mathematicians be lazy, but only if they remember that 100 is a square, right? So then, Brecken, take it from here.
10, -1 times the square root of 3.
And there's our answer. How many wound up with that answer here on 17? Good, Maddie. Did you at least get the -12 squared to 300? Okay. Number 19, a bunch of 4-3s. Now this problem's a bit of an annoyance. I'll grant you that. What did you get for your initial answer? Maddie.
8 times 3, 17 over y to the 13.
That's number 21. How about number 19? What did you get for your initial answer?
Yeah.
I was like, what did you do? Okay.
Yeah, okay. So 24 is equal to 648.
All right. Now, the thing that makes this annoying is it's a 4th root. And we're like, well, what do I do with a 4th root? Now, if this were a number I recognized, we could try to make the number smaller. If we could rewrite this as something squared, but it's not anything squared. So instead, we've got to look for a root factor that is a 4th. But there's only 1/4 we've memorized, Maddie. What's that? 2 to the 4th, which is 16. We could try to go ahead and divide the 648 by 16. 16 goes into 64 evenly 4 times, nothing left, and 16 can't go into 8. So 16 don't work. All right, and then you're like, well, I don't know any other 4ths. Well, what would the next 4th have to be, Maddie? 3 to the 4th, which would be, do it real quick, 3, 3, 3, 3. 81. Maybe 81 goes in And again, if you just look at the first digit, 8 goes into 64, class. 8 times, and yeah, sure enough, that works out. So we're going to factor this one into 81 times 8. This wasn't necessarily something we'd memorized, but something we could figure out. Take it from here, Maddie. Now what? Well, I'm just taking the fourth root of it. What's the fourth root of 81? 3. And so that gives me 72 times the fourth root of 8 is our answer. How many at least got the 24 times the fourth root of 648? Question, Noah? All right, and then do we see how to figure out how to reduce it down? Again, is it annoying? Yes. Okay, but if you're good students and you're not obnoxious, I won't give you a lot of these on the test, okay? So be good. If you tick me off, or then you'll get a whole bunch of those, and everybody fails, and it's sad. Just kidding. All right, let's take a look at number 21. You did 25, like you flipped the page to do 25. I just realized that.
I wrote down 1 for 25, and then I just looked at it and I did it.
Okay, it's okay. It's all good. It's all good. I just assumed maybe there was an extra one on the bottom of the page that for some reason I didn't assign, so you're just kind of working through. You even took time to flip the page and everything. All right, anyway, that's totally free, and Gavin has no clue what we're talking about. All right, number 21, Noah, what did you get for your initial answer?
8 times square root of...
What's the fifth root?
567.
I'm going to take your word for it because I'm not sure what it is, actually. And 567
Y.
to the 13th. Good, because when you multiply like bases, we add the exponents. $567 doesn't sound right to me. Anyone else get $567? Brecken, what did you get?
1,701.
1,701? Okay, that's what you got also? All right, let's roll with the 1,701 because that sounds more correct to me. 1701. That's right. That's what both of you had. All right, we're going to roll with it. Gavin's back there streaming at the computer. All right. All right, now we have a similar issue, right? Fifth roots. We don't know any fifth roots, right? Well, we actually do know one. Which fifth do we know, Noah? 2 to the fifth, which is 32. But this is an odd number. There's no way a 32 is in an odd number. 32 can only be in even numbers. So, again, mathematician is lazy because mathematician is smart. I'm not even going to try 32. So forget 32. That's 2 to the fifth. Maybe we try 3 to the fifth. Now, remember, 3 to the fourth was 81. So 3 to the fifth would just be another 3. 243. Let's try. 1701 divided by 243. How many times would 2 go into 17, Noah? 8 times? Let's try it real quick. Well, it can't be 8 though, because that's an even number, and you can't have an even number. Maybe let's try 7. Let's go down and try 7, okay? 7 times 3. Okay, we're off to a good start already. Oh, there it is. All right, so apparently 243 times 7 is how we'll factor this here. So we can take the fifth root of the 243. And that'll give us times the fifth root of the 7. Let's also take care of the letter now.
Y squared and Y.
There we go. And that is our answer. Anyone make it all the way there? Did we at least... Oh, you did. Fantastic job, Maddie. Excellent. I didn't see the hand right away, and then I looked back and saw it was up. Great job. Did we at least get to the beginning step? And do we understand now, again, are they obnoxious? Yes. But do we see how to work with their obnoxiousness anyway? I mean, after all, you're going to have children of your own one day. You've got to get used to dealing with them. I'm just kidding. Just kidding. I got sweet kids most of the time. Let's take a look at number 23. Oh boy, cube roots. I know cube roots. A lot better than fourth and fifth roots. What did you get for your initial answer on 23, Bracken?
The cube root of 240 cubed to the 9, z to the 18th.
I got a z to the 14th. There's z to the 8th and z to the 6th. Add them to get z to the 14th. But otherwise, and then there's one other thing. The negative kind of vanished on you there, Bracken. If there were another negative, it would change positive. But since there was only one negative, that's an odd number of negatives. Remember, it stays negative. So show the cube root of negative 240. I think it was q to the 9th, z to the 14th. Is that what we said just a second ago? Okay. Bracken, from here, let's take care of the sign first of all. Because, Bracken, odd roots always keep their sign. So my answer is just going to be negative. Let's get that negative out of there. Let's also factor 240. Now let's think about our cubes for a minute. What are some of our cubes? 9's not a cube, that's a square. Show the 2 cubed. 3 cubed. 4 cubed. 5 cubed. And so on and so forth, right? This is already bigger than half, right? This double would be 250. So I know it's got to be something smaller than that. Which of these in 240? I at least see the 8, right? Because 8 goes into 24 exactly 3 times with nothing left. So of course 8 will go into the 0 times. So I can do 8 times 30, and there aren't any other cubes in the 30, so this is indeed how we'll reduce it. And then let's take care of the letters. That's a fun one to say. 3 goes into 14 4 times. That's 12 z's. 2 z's left over. And there's our answer. I think this one's considerably easier than the last two. How many had that on number 23? You got 21 and you missed 23? Oh, okay. Did we at least get the initial answer? I know Bracken had just a little trouble because of the negative, maybe a little trouble with the z's, adding the exponents there. Questions? All right. Let me give you some classwork. So you can set your, keep your books out because we're going to get back to it in just a second. So maybe just jot these down. Go back to a round of slightly easier radicals. We've worked a few crazy ones here at the end. I want to make sure we don't get so discombobulated. There's another good word we don't use often enough. It means the same thing as befuddled, if we're going back to earlier. But don't you be so discombobulated by the hard ones. You forget how to do the easy ones. And again, the big thing is at the end, class, that's when we need to reduce, which often means factoring. So I think the actual multiplication part is easy. We need to make sure we don't forget the reducing at the end. multiply coefficients, multiply radicands, and then the all-important step at the end, reduce, because your answer is usually going to be quite large because of the multiplication. Is finished. For sake of time, check the answers to the ones you got done. Should have gotten 6 times the square root of 6 for the first, 60 times the square root of 2 for the second. Good. 4 times the cube root of 3 for the third, 8 times the square root of 3 for the fourth, 16 times the square root of 5 on that fifth one, and then if you had time to get to the last one, 24 times the cube root of 5. How many got all the ones you did correct? Okay, only Brecken. Noah, Maddie, which one or ones did we miss?
Third.
The third one here. Okay, Maddie. The fourth one. All right, I assume you initially got the 4 squared of 12. Okay. Noah, I assume you initially got 2 times the cube root of 24? Okay. Did you factor 4 times 6? Okay, yeah, again, cube root, we don't care about 4. We want 8 times the 3 to get the, okay? All right, and good job, Brecken, on yours. Questions on these at all? All right, back to your textbooks. I want you to do 18 and 24. 18 and 24. They're on page 287. Page 287, 18 and 24. sake of time, go ahead and put your pencils down. Let's see how you did on these. Pencils down. Number 18 should have been pretty straightforward. 6 times the square root of 490, right? And 49 times 10 kind of should have been screaming at you. Pull out the 7, 42 times the square root of 10. Everybody good on 18? All right? Yes, okay, good. Number 24 is just nasty, right? Now, there is something that I realized later could have saved us some time and trouble. Do you see on number 24, look at the first radical, the cube root of 64. And I was kicking myself afterward for not just making that a 4 times the cube root of g to the 5th h to the 13th. In some cases, it may be best to take roots earlier, because otherwise you get that. And if you've taken the 4 times 10 is 40, you see 8 times 5 easily. But I tell you, I had to make a pretty long list to see 512. And I saw 512 times 5, so took out the negative 8 times the 10 gave negative 80. I left the 5. 3 goes into 13, 4 times 1 left. 3 goes into 16, 5 times 1 left. But yeah, that would have made life so much easier if I just seen, hey, the cube root of 64 is 4. Let's just get that out of there right from the get-go so I don't have this massive number. So sometimes maybe better to reduce or take a rational root, especially earlier on. Questions on 24. How many at least got that initial step? All right, and then again, the reducing is just nasty. Did anyone finish it and get the right answer? Okay, you were on the right track. I mean, you figured out the 512?
Well, I did 64 times 40.
Okay, 64 times 40 would have worked, and then you could have taken the 8 and 5 down from the 40. Anyone else on the same track there, 64 and 40? All right. I saw the 64 because I remembered multiplying it earlier, like, oh, and that's when I was like, why didn't I? But I already written the negative 2,560. I didn't want to erase and write something else. I am that late. Then I'd have to show the whole problem all over again. I was like, nah, I'm too lazy for that. Questions on that? Write this down in your notes if you would. I want to show this to you, but 2 times the cube root of 5 times 6 times the square root of 3. And on the surface, we would say you can't multiply those because they don't have the same index. And you have to have the same index. Well, you know how we can make indexes smaller? By writing something as a power, and then we can cancel something out of both index and exponent, because really it's a fractional exponent anyway. Not only can you take something out of both of these numbers, you could put something into both of those numbers. Does that make sense? Literally, we would unreduce the radicals. So the question is a cube root and a square root. 2 and 3 can both become what number? 6. So what I would want to do is I would want to turn this into 2 times the 6th root of something times 6 times the 6th root of something. Go and write that initial thing down in your notes. I mean, this is Algebra II level, but I wanted to show it to you here now. I just want to preview it to you. Now, obviously, class, to turn the 3 into a 6, I would have to multiply it by 2. And that's what I'd have to do to the exponent also to make this not a 5 to the first class, but a 5 squared. Or in other words, 2 times the 6th root of 25. So here, what do you suppose we do to 6 times the square root of 3 to the first, Noah? Good, 3 cubed, or in other words, and I like that he did it in his head, and that's what the push will be next year in Algebra 2, is to do it in your head. And now do you see that we have made like indices? We didn't have it to begin with, now we do, and now we can multiply. And 2 times 6, of course, is easy, class. And 25 times 27 is not. Picture 27 quarters. Remember, every 4 quarters is $1. What is 25 times 27? Okay, 27 quarters. How much money is that? How many stacks of 4 can you make out of 27? 6 of them, right, with a stack of 3 left over. So $6 and 3 quarters. $6.75. Again, that's how my brain works, at least as far as 25s. Everything comes back to quarters when it's 25s. And here's the neat thing is, if you have to blow the numbers up, it will almost never reduce. If you were curious, though, you say, well, I know 2 to the 6th class is... I have to take another one of these quizzes. 64. Which, okay, 64 would go in with 3 left over. Can 64 go into 35? No. Okay, what about 3 to the 6th? Well, remember earlier we said 3 to the 5th was 243. So 3 to the 6th, well, that would be 729. That's too big to go into 675. So sure enough, it doesn't reduce at the end. And again, that's often the case when you have to make the indices larger to make the multiplication happen. But no, that's what we would have to do in Algebra 2 next year. All right, your extra credit for this evening is to do page 174, word problem 6. Page 174, word problem number 6. You do have a test coming up on Wednesday of next week. That's in lesson 169. Wednesday of next week, we have a test coming up. That's in lesson 169, and it will cover through multiplication of radicals. So tomorrow and Monday, we'll be wrapping up multiplication. We got to steal a few new things we want to do with multiplication. Multiplying binomials, for instance, that have radicals in them. And then we will also be reviewing on Tuesday, taking the test on Wednesday. All right, have a wonderful rest of your day, and you are dismissed.